Now I want to talk about another solution to the maximum frequency stack. So in fact, this is the cleverest solution to this problem that I know of. It exploits some very interesting observation about stack. So this is really coming up with this solution requires sort of in-depth understanding of the stack, but hopefully it's not too hard to explain how it works. So recall that we want to, when we pop the values first by the number of times they are added to the stack, and then by the order. So then, in some sense, what we have is actually multiple stacks. So you can think of, we have a one stack for each number. If it's the first time some element is added, it's added to the first stack to the stack at layer 1. If it's the second time for a value is added, then we add it to the second layer. And if the third time it's something added, then we add it to the third layer. As you can see, this has to grow sort of one by one. So we cannot jump from 3 to 5. We have to first add something 4 times before we can add something 5th time. So if we have that, then for every when we pop, we will look at the highest level, and then we pop the last value at the highest level. So here I'm trying to use this table to illustrate the state, but I guess the best way is to do it by animation, but I'm a little bit lazy here, so I'm sort of using the multiple time state together, but let's just go through it. So the first push, we push 5. So here I use A, B, C, D to indicate a different push so that we can distinguish the different 5s. So when we push 5, so we call this 5A, it goes into the first level stack because this is the first time 5 is added. And if we push 7, then because that's also the first time 7 is pushed, so then we add it to the end here. If we push 5 again, now because 5 is already added once, we will need to put 5 here in the second layer. And then when we put 7 again, because 7 is already added, 7B goes here. And then when we push 4, because this is the first time 4 is added, so 4 is added here, so at the tail of the first one. And then when we push 5 again, this is the third time 5 is added, so 5C goes here. And when we pop, we will look at the highest level. So at this point it's 3. So then this 5 goes, so 5C goes. So then the second pop, we will be looking at the second layer. So this 4B has not occurred yet. So then what happens is this 7 will be popped. So the second pop will return 7. So suppose the next operation is push 4. Now this is the second time 4 is pushed. So then 4B will go to the end of the second stack, which is this position. So at this point 7B is already gone. So 4B takes this position. And this time I think 5C is also gone. So the next pop will actually pop this 4. So because at this point the 5 and 4, they each have 2 times. So at the end of this sequence operation, there are 2 5s and 2 4 and 1 7 in the stack. And this 4 is the most recently added. So next pop will pop with 4. Next one will pop this 5. And then it's this 4, 7, 5, this order. So to implement this, first we need a vector of stack or array list of stack if you implement in Java. And second, we also, given each element, we want to quickly find out what is the highest level for that element. So then we know when we add it, which layer does it go. So for example, at the next point, if we push 5 again, we know then this should go here because we already have 2 5s. So then what's needed is a map from every element to the current highest level. So then when we push that element, we will figure out which layer of stack should that element go and then update that level. So by using this a layer of stacks and the additional map, we can implement this. And this logic is easier, but it's sort of yeah, it requires sort of this insight of using a layer of stack or stacks of stacks, if you will, to implement this.